for having me. I'm Xiaozhe from ETH Zurich, and now I'm going to talk about DeltaZip, our recent work on efficient serving of multiple fine-tuned LLMs. Let's start with a little bit of background on this recent LLM development. So we start with trillions of tokens as a general corpus at the pre-training data set. And we start with tens or sometimes hundreds of billions of parameters at the empty model. And then we conduct the so-called pre-training process, and we get the pre-trained model. But we don't stop here. Actually, we will start with some specialized data, probably thousands or millions of tokens, and we perform the so-called fine-tuning process, which is a lot cheaper than pre-training. It costs probably thousands or sometimes millions of GPU hours. And then we get a bunch of different specialized models, particularly trained on some downstream tasks. For example, coding, some writing, and very popularly, some chatting models. And then we come to a problem on how we can serve those specialized models in a more cost-efficient way. This will be the topic for my work today. This is particularly challenging because if we look at the distribution or the request pattern of those models, these are pretty bursty and sporadic. So here, this figure shows 20 different models from an online chatbot arena service for a duration of 1 week. Those darker red area indicate the time when these models are called more often, and those lighter yellow area indicate the time when those models are called less frequently. And as you can see here, the request pattern is really bursty, unpredictable, making it hard to predict which model will be called at a certain time so that you can preload the model to your accelerator. In the meantime, people online are asking if anyone is offering a serverless solution to host those fine-tuned open models that has minimal code start time, latency, and where you can pay by tokens. And also, even for those big companies who are dedicated to serve those models, they are asked by the customers, why do I need to pay 24/7 for an expensive GPU to use my fine-tuned model when I don't have to? I spend a lot of money, and it's just a waste. So this is a question that we want to answer. What can we do beyond over-provision enough very expensive GPU servers to serve those specialized models? A very naive idea that we have is that we can load the model on demand. So when a request comes, if the model is not in the accelerator, we load them from disk to the GPU to serve the request. Unfortunately, this doesn't work well. This doesn't scale. The main issue is that we will be bounded by the disk bandwidth. Even a pretty decent SSD today can only offer us around 7 gigabytes bandwidth. And if this is far from enough. If you consider a 70 billion parameter model in half precision, that will be 2 bytes per parameter, and in total, it takes more than 140 gigabytes memory. And if you want to load that model from your disk to your GPU, it will take more than 20 seconds. And your latency will be definitely more than 20 seconds. And if you have 10 concurrent models being requested at the same time, you won't be able to maintain a satisfactory latency. How can we reduce this by a factor of 10? Another solution that people are exploring is called low-rank adaptation. Simply put, this is basically train a small additive adapters instead of fine-tune the entire model. However, this requires a new training paradigm. So for your customers, you will ask them to train the model in this particular low-rank adaptation strategy. And this approach won't work for those existing, already trained, already fine-tuned models. And more importantly, we found on those complicated tasks particularly, those low-rank adaptations still underperforms full fine-tuning. This is not only from our own internal benchmark, but also from external sources that we found online, from Databricks and also Google. So we can be a bit more concrete here. How can we reduce this by a factor of 10 for full fine-tuned models? This is the question that we want to answer today. Our idea is that instead of swiping in and out the very huge entire models, we can compress and serve the model deltas. The motivation of this is that we observed that many fine-tuned models actually stem from the same base model. This is because pre-training is very, very expensive. It probably costs tens of millions of dollars to pre-train your own model. But fine-tuning is much cheaper. Almost every lab can fine-tune their own large language models. And we believe that the delta between the base model and the fine-tuned model is highly compressible, or in other words, fine-tuning only slightly perturbs the model weights. Is this really the case? Let's take a look at the distribution of the model deltas. We start by plotting the weight distribution in the base model and in the fine-tuned model. In the blue plot here, we plot the distribution in the base model, and in the yellow plot, we plot the distribution of the fine-tuned model. As you can see here, the value fluctuates quite a lot, but the outliers almost appear at the same place. So if you take the difference, simply take the difference, you get a much smoother distribution of the weights in the delta matrix, and they appear in very low magnitude. And we conclude that the base model and the fine-tuned models themselves are pretty hard to compress, but the model deltas are relatively easier to compress. Inspired by this observation, we built the system called DeltaZip. Essentially, we multiply the serving of multiple fully fine-tuned models. And today, I will be focusing on two parts. One is about our compression algorithm and pipeline, and also how we make it run fast. Our compression pipeline is a combination of different strategies. We include sparsity and also low precision. We start by extracting the delta matrix, assuming we have an 8x8 matrix that could account for 128 bytes. And then we first apply structured pruning, which means for every 4 consecutive values, we remove 2 of them. We set 2 of those values to be 0. And then in order to store this weight matrix, we don't have to store those zeros anymore. Instead, we could store those non-zero values in half precision only. And in addition to that, we store the indices matrix to indicate where those non-zero values are. And we only need 2 bits per value. And in total, this brings us 1.7 times compression. And then we can apply quantization. So basically, for every non-zero value in this half precision weight matrix, we can quantize them and use a lower precision like 2-bit or 4-bit to represent the value. And if we use 4-bit, this brings us 5 times 3 compression. And if we use 2-bit, this brings us 8 times compression. And at the end, we apply a hardware-efficient lossless compression algorithm, which could further increase the compression ratio. And at the end, from end to end, we achieve 10 times compression ratio. And in order to serve the request more efficiently, let's recall that we are playing the role of a cloud provider where we could have requests from different models from different customers. And even though in our context, they might be different models, they share the same base model. So we can decouple the computation of the base model and the delta part. So for many different models, they share the same base model. We can increase the batch size for the computation of the base model part. That means by increasing the batch size, we improve the GPU utilization of this part of computation. And then for this delta part, we could apply a low precision matrix multiplication to further improve the GPU utilization. In order to achieve this, we designed our own kernel to do so. Basically, our kernel performs a bunch of different matrix multiplication in one kernel launch. And here, our idea is that in order to do a matrix multiplication, we only move the low bit weights or compressed weights from the GPU HBM to the computer unit. And then we immediately decompress there, perform the matrix multiplication, and write the results back to the GPU HBM. So we fuse the dequantization and actual matrix multiplication. The reason why this is fast is because we significantly reduce the data movement between the GPU HBM and the computer unit. And this is particularly important in the process of LLM serving. And furthermore, for every matrix multiplication that we are doing here, we use a sparse tensor core, which is natively supported on modern GPUs and brings us 2 times peak flops. And here, since we are having multiple different models being called at the same time, and therefore we need to do multiple different matrix multiplications together in parallel, and we can do this in one kernel launch from CPU with our design. And then let's talk about some experiments. In order to evaluate the performance of the system, we conduct the experiment from 2 aspects. One is about model accuracy after compression. with our evaluation, we conducted experiments on multiple different downstream data sets, and we found our algorithm could retain comparable accuracy with 6 to 10 times compression ratio. So here, 3 different colors represent 3 different downstream tasks. And as you can see here, even if we have a compression ratio of more than 10 times, we basically remain the same downstream accuracy compared to the uncompressed model. However, if you apply the same algorithm, but on the entire model, your model quality will drop significantly after the compression ratio of 4. So basically, if you have lower than 4 bit widths per parameter, your model quality drops will be significant. And that's also the reason why not many people are serving those models under 4 bit. Another advantage of our algorithm is that we do not require any retraining or recovering after the compression. So basically, in order to compress the model, we only need to run some very cheap inference process. And from our experience, this is very cheap. In order to compress a 70 billion parameter model on a single 3090, this only costs around 20 minutes. And our algorithm scales from a few billion parameter models to 70 billion parameter models. If you are interested in more details, please refer to our paper. And we also evaluated the end-to-end performance, and we found across different workloads, we achieved 2 to 12 times improvement for end-to-end latency, and similarly for throughput and also SLO. And the improvement is more pronounced in time to first token, because we really reduce the data movement that we need to do in order to move the model from disk to the accelerator. And there are more details in the paper if you are interested. And we have introduced the concept of delta compression back in 2023. And since then, we have seen great momentum from the research community. We have seen lower precision as low as 1 bit parameter. And we have seen higher sparsity as high as 90%. So this shows those delta parameters are really over-parameterized and can be compressed more aggressively. And we are very excited to see this idea can be applied to many new different models. For example, mixture of experts. And most recently, we have seen some papers that show that those quantized delta is safety keeper. And some people are proposing even data-free compression for these delta parameters. And today, what I'm talking about is more about a system and algorithm co-design. The idea that we use here, including structured sparsity and quantization, are all hardware efficient and can be run fast on modern hardware. This is our focus from our group. In summary, I hope I have conveyed the message that those model deltas are heavily over-parameterized, therefore highly compressible. And to our best knowledge, this is the first work for multiplex full-parameter fine-tuned models, particularly LLMs serving. And the approach we take is a system and algorithm co-design. We have not only the compression algorithm, but also kernel optimization. We extend continuous batching and model parallelism to our context. And also, our system is open source. And actually, this is just the start of the story. We are excited to do more in this direction. So first thing that we want to understand is about joint compression. There are a bunch of different components in the LLM serving process. For example, there is KV cache, there is activation, there is a concept, the notion of base model, and the delta. Which component is more amendable to the compression is something that we want to understand and navigate in this space. And also, in the context of multi-tenant model serving, scheduling is a quite straightforward and natural question that people are wondering. If you are serving a bunch of different models, starvation might be an issue, and we want to understand how we can mitigate this issue. And also, we are seeing more and more heterogeneous and newer hardware being applied to serve LLMs. For example, Hopper GPU supports native FP8 computation, and Blackwell supports native FP4 and FP6. And we also have some FPGAs that could support arbitrarily low bit width computation. We are excited to see how we can leverage different hardware to be more efficient in this LLM serving context. And there are other compression techniques that we are exploring and trying. For example, matrix factorization, which stemmed from this low-rank adaptation territory, but we believe this can be further applied as well. With that, I conclude my talk, and I'm open to questions.